So, welcome to the last lecture on logic for computer science. So, we have let's just briefly recapitulate what all we have done. Well, there was an introduction in which we we actually looked at the notions of what is logic, the notion of validity of arguments. We made it clear that logic is concerned only about the form of reasoning and not really about the content. And then we also spoke about reasoning, truth and validity, and we showed how we have gone through many examples where there were fallacious proofs, and we have shown how you can sometimes derive false conclusions from from true premises, and on the other hand we can always, even with sound reasoning principles, you can produce false conclusions from false premises. So, that is so in that sense logic really has to do with only finding logical consequences of the premises that we or our assumptions and or our hypotheses, so to speak, and it is not really concerned with the actual truth of statements that one might make about any structure or about the universe or the world in general. So, and in particular we focused on first order logic by starting from propositional logic, the propositional connectors, propositional logic or also sentential logic. We defined the notion of truth and falsehood. So in that sense it is a mathematical it's a mathematical approach to logic, where we essentially studied logic also as a branch of mathematics rather than really as what was originally intended, namely that logic should have been the foundation for mathematics, right. So instead we just treated it as a branch of mathematics. Right, and then we started with Boolean algebra, and we went through all these, the propositional logic syntax, the usual propositional connectives. Then we also showed that there were some. So there's also an algebraic treatment of logic derived from Boolean algebra, essentially propositional logic. We spoke about identities, normal forms. Then we also gave an algorithm for checking tautologies, and we use this tautology checking also to validate or falsify arguments, right. And we showed that there were several techniques. You could use truth tables, you could use various other logical consequence mechanisms. We could also we could also use proof theoretic mechanisms, and which is what we did in our Hilbert style proof system. And from the Hilbert style proof system we came up with the notion of formal theories, especially the monotonicity property, the compactness property, substitutivity, soundness of a formal theory. These are all axioms as a subset of the language. We gave a set of inference rules of these various forms. We spoke about axiomatic theories and decidability, and we actually went through these rule patterns, and which as you can see are completely syntactic, and therefore they are not really concerned about underlying content of the sentences about which we are reasoning, right. Okay. Then we also showed certain important properties about formal theories and about the Hilbert style proof system. We showed for convenience we could derive a large number of new rules, we could use them, you could essentially plug in the proofs, and therefore the substitutivity of rules, and we showed a convenient way of introducing assumptions and discharging assumptions through the deduction theorem, which was and its converse. So we showed that we could move between conclusions, between proof conclusions and assumptions that we make, and which is in fact the deduction theorem actually tells us something about the normal reasoning practices that we normally have, that we normally employ when dealing with proofs in mathematics. Yeah. Okay, and moving from the Hilbert style proof system, we also showed its soundness and completeness. We moved on to the soundness of the Hilbert style system. We showed that every instance of every axiom in the Hilbert style in the system H naught, which is the Hilbert style proof system for propositional logic, is a tautology, and the modus ponens rule preserves tautol logosness. In particular, it also preserves it preserves tautol logosness, and therefore, the notion of deriving conclusions or fresh facts from a set of assumptions which are held to be true uses the modus ponens rule, and we showed that this system is also complete in the sense that uh, every tautology in propositional logic, okay, the completeness theorem just says that every tautology can be derived as a formal theorem of the Hilbert style proof system. And in particular, what we did was its relationship to this to the semantics of propositional logic, which is a language, was by actually simulating the truth table. And what we showed is that by this lemma is that every truth table can actually be simulated as a logical proof in the Hilbert style system. Going on from the Hilbert style proof system, um, we also looked at analytic tableau, which gave a convenient analytic tableau, and again resolution method, which gave convenient methods of actually proof which can be automated. And the tableau and the Gentzen natural deduction system share this common feature that they actually break up a formula into essentially subformulae depending upon the kind of operators at the root. So, in that sense, in propositional logic, the, the tableau rules are such that every tableau would actually be finite, and we showed that the tableau system was also complete. Moreover, by being structurally inductive, by the rules being structurally inductive, we also showed that it is possible to automate this for a propositional theorem prover. So, we could do tautology checking, validity checking, and so on, and all those problems for propositional logic are actually decidable, are algorithmically decidable. So, we showed how the tableau rules can be used to come up with tableau proofs. We showed the consistency. We showed how unsatisfiability can be proven through closed tableaus. We also had the notion of Hintica sets, and we showed using Hintica sets that the tableau method is also complete. We also, and then we had the compactness theorem, which showed that in order to prove unsatisfiability of infinite sets, it is sufficient to find a finite subset which is unsatisfiable. So, this is a property of this is what is known as a property of finite character, which the compactness gives us, and which unsatisfiability also satisfies, right. Um, then then moving on to first order logic, we actually defined this. We went through essentially the same processes, but now it is more complicated because the underlying model of truth table, which is finite, does not hold anymore. I mean, and we are looking at essentially modeling structures expressed mostly algebraically, and we are looking at using syntactical methods to prove facts about complicated algebraic structures given their and classes of structures which share a common signature. So, the notion of signature, the notion of substitution, and therefore, an extension of the Hilbert style proof system for first order logic. Before that, the semantics of first order logic therefore gets considerably the syntax and semantics of first order logic become considerably more complex. You can see that we had to define a separate set of symbols of countably infinite collection of variable symbols, function symbols, the notion of a signature, the term, and actually the sort of each element in a signature, which is given by a sort S, by a sort symbol S, and which you can think of loosely speaking as being related to the notion of types in programming languages. So, essentially a single sorted signature is, or a one sorted signature is what we considered throughout, and it referred to basically a simple algebraic system consisting of a single set, and all elements essentially belong to, purportedly or putatively belong to this set, and this set might be, and since we are looking at classes of structures, we did not specify this set explicitly, but instead just use a syntactic symbol called S for a sort. Yeah. Okay. So, then as we saw, the semantics of the semantics of predicate logic therefore also gets considerably more complex, since we had to deal with structures which satisfy certain signature properties, and essentially first order logic deals with properties of structures. Actually, it turns out that it deals with properties of classes of structures which share common signatures. So, in that sense, first order logic is parameterized over the signature, and we are essentially looking at the axioms of such structures. So, we had various examples. We also showed, so we had the notion of an interpretation of the symbols of a first order language over a signature sigma. We needed the notion of evaluations, and there from there and therein we actually defined the notion of truth of a formula with free variables. So, where the truth might depend, the truth of the formula might depend on the values assigned to the free variables, and so therefore, in addition to the interpretation, you also require the valuation. So, we had a formal semantics for the evaluation of terms firstly, and then we gave a coincidence lemma, which essentially, since variables are an infinite set, we had to show that we had this coincidence lemma, which essentially said that under two different interpretations or under two different valuations, if the variables mentioned in a term are the same and the valuations for all those variables, that finite set of variables is the same in both valuations, then the values of the terms would also be, the values of the term in the two valuations would be the same. So, we had the notion of variance, and then we gave the semantics of first order formulae, in particular that of the two quantifiers, which are each of these quantifiers is actually parameterized on a variable. The notion, therefore, it brought in the notion of bound variables and free variables and substitutions. We also showed that you can have a coincidence lemma for formulae, you can replace valuation variants by substitutions, and then what we did was we used these notions of, we used the same notions, we extended the notions that we had for propositional logic to first order logic. We defined the notions of models and satisfiability and validity based on structures and substructures, and then we extended the Hilbert proof system to first order logic, for example. Yeah. So, we had these extra rules essentially dealing with quantifiers. We also had we also had derived rules in this case, but you could for example, we had these, in addition to the derived rules, we had we also had the notion of equality, for which we gave some axioms, but more importantly we showed that the rules for existential quantification, for example, the existential elimination rule and the corresponding derived rules are not, it's not the existential introduction is a derived rule, however, existential elimination is not a derived rule. However, what we managed to show is that you can, every proof by existential elimination which uses the existential elimination rule can also be transformed into a proof which does not employ the existential elimination rule. In this process, we also required a deduction theorem. We showed that there are restrictions on the application of the deduction theorem. So, essentially the deduction theorem applies mainly for sentences. So, the quantification over free variables and therefore generalizing from free variables or instantiating free variables is a subtle issue, and one has to be careful about generalizing on, for example, existential variables by a universal quantifier. So, further we also the other proof procedures for propositional logic were extended to resolution, for example, and tableaus. So, we did both. We also showed that our Hilbert style proof system was sound and complete, the tableau method was sound and complete. Again, we extended the notion of Hintica sets, first order tableau and Hintica sets, and we showed that these are both sound and complete. And we proved the soundness and completeness of the Hilbert style proof system. We also proved the soundness and completeness of resolution. What we showed in particular was that resolution was refutation complete. So, which means it is not necessarily clear that you might be able to derive all logical consequences, but what is necessary, what is true definitely is that you can always refute the negation of a logical consequence and prove it. So, in that sense resolution was refutation complete. Yeah. So, this is what we so therefore, this gives us directly methods for automating the notion of theorem proving, automating the notion of proof even for first order logic, either through resolution or through tableau. The Hilbert style system does not necessarily permit itself to be automated so easily. On the other hand, resolution and tableaus do. And with that, we have we showed some, we also gave some applications of these first order theories. First, of course, is that logic programming is essentially something that is based on resolution. A particular implementation of logic programming is Prolog, and we looked at some Prolog code too. There is some Prolog code that here for example, and we showed and there are however there are certain pragmatic reasons why Prolog is really different from logic programming. First of all, Prolog does not it treats negation as a failure of proof rather than negation as an operator. So, that is one thing, and moreover Prolog, all Prolog implementations which follow what is known as the Warren abstract machine model actually tend to be unsound because of certain problems with substitutions and unification, most general unifiers. Then we looked at other applications. For example, we also looked at the verification of imperative programs, the notion of a predicate as notion of a programming language or a programming construct as not just as a state transformer, but as a predicate transformer, and that is what we looked at. So, this is like generalizing the notion of meaning from single states to sets of states, and sets of states essentially signify a property and therefore a predicate, and so we actually extended this notion. We came up with these notions of correctness assertions and total correctness assertions, and we have given some examples, yeah, on the verification. We also at the end, so we had these rules, the notion of a loop invariant, the notion of a well ordered set or a bound function which basically traverses down a well ordering in order to prove termination of these programs. Finally, we ended with an open problem, the collapse problem. So, what we would like to do now after this wrap up is to look at, okay, why first order logic? What about higher order logics? What about second order logic? The other questions are, what about, we looked always at one sorted signatures, can we look at many sorted signatures? In what happens to the first order logic of many sorted signatures, for example? What happens to higher order logic? These are some questions that go beyond the scope of this course, but we will just touch on them. So here is a simple summary of what we have done: a mathematical treatment of the essentials of reasoning, a rigorous treatment of first order logic, applications basically to theorem proving, logic programming and program verification. We also gave some illustrations of the power of first order logic. For example, we required just two axioms for equality to axiomatize all properties of equality, and we showed basically that in many cases you can come up with first order theories which are sufficiently powerful. But we also showed that there are, first order logic has certain severe constraints. For example, there is a lack of distinguishability. One of the things we did, so the non-standard model of arithmetic that we proposed allowed for the axioms of number theory to have models which are not isomorphic to the standard model of arithmetic, as we standard model of the natural numbers with successor as we are used to it. And the fact that it is that there are models which are not isomorphic to the standard model indicates that the power of distinguishability that first order logic has is perhaps not enough, and it does not necessarily capture exactly all the properties that one would like, which can characterize a unique model. So, so essentially in these non-standard models, what we showed is that in addition to the existing standard natural numbers, one could actually have whole copies of classes of integers on both sides, and they would still satisfy the same standard axioms of number theory. And this means that the first order theory of numbers with the axioms that we have got does not have that fine discriminating power which can exclude all those copies of integers, what were called Z chains, right. So it could not actually eliminate them. I mean, so that fineness of expressiveness of the axioms is something that is absent in first order logic, especially the first order theory of numbers, and therefore there is an obvious question of how does one proceed. The other thing is that, for example, the first order theory of numbers with or piano arithmetic, for example, includes an property of the principle of mathematical induction, which in the first order case is extremely restrictive, right. Whereas piano's original intended principle was for all possible properties of all possible subsets of numbers which might only be characterized by which might be parameterized by some single integer or natural number, right. So let us look at certain extensions. One is, one possibility is, one thing is, look at this property of well orderings. By the way, this should be for every non-empty subset. Every non-empty subset of a well ordered set has a least element. Now this cannot even be expressed in FOL because it requires the power of second order logic, because we are essentially saying that one should be able to, given a set S, the well ordering principle along with the first order predicate less than or equal to, what we are saying is that the well ordering principle essentially says that it is not just about individuals of S, but subsets of S. So if I have any non-empty subset of S, then this non-empty subset of S has a least element. Okay, so how would one express this? One would essentially express this by saying for all x such that there exists some z such that z belongs to x. So, this indicates that x is a non-empty set for all x such that there exists a z such that z belongs to S. This indicates that for all y, there exists an x, this is a small x, such that x belongs to x, and for all y such that y belongs to x, we have that x is less than or equal to y. Now, here it is important to see that this x, this capital X throughout actually represents subsets of the domain of discourse. Yeah. And this is not something that we allowed in our first order logic. So, even a very basic principle like well ordering cannot be expressed in first order logic, and it requires at least the power of second order logic. And in second order logic, essentially what we are allowing is quantification over over sets, or quantification over first order properties. If you were to think of a subset of S, you can think of it as a unary predicate representing a property. So, while it is true that every unary property has a characteristic set. So, for any property phi, so let us say phi is a first order property, then I can think of a characteristic set of phi as being defined as the set of all elements x such that phi of x is true. Right. This, given a universe of discourse U, this set is a subset of U. However, not all subsets of U may be characterized by properties. However, in a second order logic, every property, every first order property is characterized by a subset. So, what we mean by this second order property is that now we should be able to allow a quantification over subsets, or over, or even firstly over properties definitely, but more importantly we would require quantification over subsets. So, one of the reasons I am saying that while every first order property has a characteristic set, a subset of the universe of discourse, not every subset of the universe of discourse can be characterized by a first order property, because if you look, if the universe of discourse were say the natural numbers, then the number of subsets of natural numbers is uncountable. However, our language of first order properties has only at most a countable number of formulae. So, therefore, while every property, every unary property is characterized by a subset of n among the natural numbers, not every subset of natural numbers can be expressed as a unary property. And a simple diagonalization argument would show that this is in fact true, that not every property of the natural numbers is expressible in first order logic. Okay, the other thing, for example, transitive closures are not expressible, and this means that for example, the first order theory of directed graphs cannot cannot even characterize some of the most elementary properties we see in graph theory books. Okay, so moreover, so one possibility is to actually tackle the notion of sortedness. So, there is one thing. So, all our treatment was based on a one sorted term algebra, and it often does not address the interesting problems of a mathematical theory. For example, the first order theory of directed or undirected graphs in any graph theory book, you would want to count, for example, you would want to make statements like the directed graph is such that every the sum of all in degrees of the graph is equal to the sum of all out degrees of the graph. So, that includes counting, and in the first order theory of graphs there is no notion of counting. So, one possibility is to actually import also the theory of numbers and counting into the first order theory of graphs, and then try to axiomatize, try to derive properties of let us say directed or undirected graphs. So, the first step towards doing this is to actually dispense with a one sorted term algebra and allow for a many sorted term algebra, right. Secondly, if you look at this second order formulation, this is also something, if you can think of, instead of looking at it as a structure of a set S with just the less than or equal to, if you also thought of this as S union the power set of S along with the less than or equal to and maybe some other properties regarding sets, then we could actually begin to think in terms of replacing this x, this capital X by an individual here, and so an individual here could denote either a single individual element from S or a single individual subset of S. And of course, then what we need to do is we need to be able to distinguish between these two kinds of individuals, and that is something that will be part of the many sortedness. So, in particular second order logic could then be transformed into a two sorted first order logic, and that is what we will see, we will look at it. We will look at this problem now, but first let us formalize the notion of a many sorted logic. So, we had the notion of a one sorted logic, one sorted signature. Now, let us look at a many sorted signature. This is important because for example, most of our programming languages and the compilable programs that one can write in our programming, in our general purpose programming languages, are all essentially terms from a many sorted algebra, because of the fact that firstly our programming languages abstractly allow us to have many different kinds of elements, integers, booleans, reals, characters, strings, and then functions defined between them, relations between them, and so on and so forth. So, in that sense our programming language starts with a signature which is already many sorted. Yeah, there are at least four or five different kinds of basic elements, basic sets from which our programs, on which our program terms are defined. Yeah. So, we will call these different kinds as sorts, right. So, we have, so assume given a finite non-empty set S of sorts with S equal to Si 1 less than or equal to I less than or equal to k. So, this single symbol S here, which I used for one sorted signatures as just a symbol, now gets replaced by a collection of such symbols, one for each sort, one for each kind of element that we are talking about. Our set of variables also get slotted into various slots. So, we might think of the set of variables V as being divided up into countable disjoint subsets of variables, where each variable has a predefined sort associated with it, and of course we need always a countable set for each sort, and so we will assume that our set of variables V is actually this disjoint union of variables Vi where for each sort Si in S. And then we have a countably infinite collection of function symbols as we had here, and that now what we allow our function symbols to do is something that you will see later. It will allow us to take terms from different kinds of sorts and give you terms of yet another kind of sort. For example, it is possible to take terms from the integers, two terms from integers and give you a boolean. Their less than relation can also be treated as a function, for example, if you allow booleans as a sort. Yeah. And then of course an countably infinite collection of atomic predicate symbols as usual, and then we, because of this fact that we need to slot variables appropriately, we also allow for quantifier symbols, one for each sort. Yeah. So this, so if you were to look at this, so I have put a subscript I here. Essentially to say that we also have, for different kinds of elements, for different kinds of variables, we have different quantifiers. So now a many sorted signature is something in which you have your functions f, which might take, let us say, which might be an Emery function taking elements from m possibly different sorts and giving you an m plus 1th sort, which is also different. Your predicates likewise could take could be parameterized on n different sorts, and still and therefore they allow you to explicate relationships between the various sorts. Okay, and then of course for each sort it might be necessary to also have a binary equality relation. Equality is rather special, as I told you before, because very often we might be talking of two putatively different elements by giving them different variable names x and y, and then we might have to prove that they are really the same element, in which case equality becomes a necessary predicate, binary predicate for each sort. So, we will have this equality relation subscripted by I to denote an equality relation on the sort Si, right. Okay, now our terms are essentially like this. So the set of terms T sigma is the disjoint union of all possible terms which are being classified into sorts. So every term in our term algebra now has a sort associated with it, and that sort is one of those sorts taken from the set S. So for example, each variable xi belonging to the variable set Vi is of sort Si, right. Now if I had a function f which was of type Si1, Si2 to Sim going to Si0 belonging to this signature, and if I had terms T1 to Tm which were respectively of these sorts, which have been defined as being of type being of sort Si1, Si2, Sim respectively, then the net result of applying this function on these terms is to give you a term which belongs to the sort Si0. So that is what we are saying here. Each variable xi is a term in Ti sigma, a fact usually denoted by this. So this is our standard, this is like our type declarations in programming languages, and in the case of f T1 to Tm, it belongs to the sort Si0. So therefore it belongs to the term of set, the set of terms Ti0 of sigma. And once all terms have been classified in sorts, the set of all terms is just this huge union of terms for each sort. You just sort of agglomerate all the sorts of all the terms of different kinds into a single set, and that you call that the set of terms, right. So, then a many sorted predicate logic then just has a syntax of the logic which is exactly as before, and which we have seen before, and so I will not go into it. The semantics now requires an S sorted signature with a non-empty domain AI for each sort SI, right. Then we just extend the semantics in a simple way. Similarly, it becomes a little tedious to write it, but otherwise the extension is fairly obvious, and this semantics is then a minor extension of essentially the one sorted case. Once we have this many sorted predicate logic, we can actually do one thing. Firstly, a second order logic such as this, which requires as you can see, basically this notion of well ordering, it is a second order predicate, simply because we need to be able to have two different kinds of individuals. One kind of individual ranges over the set, over the set S of the universe of discourse, and the other, the capital X's, actually range over 2 raised to S, the power set of S. So, we can think of this as a two sorted algebra, as a two sorted structure with a one sorted predicate, with a first order predicate less than or equal to. And what we may do is we may just think of second order logic as simply a two sorted logic with predicates parameterized over both individuals and sets of individuals. So, in that sense we have reduced second order logic to a two sorted first order logic. There is actually a further reduction possible. Any S sorted predicate logic may be reduced to a one sorted predicate logic by introducing a fresh set of unary predicates, and I am calling this set of unary predicates is Si. To essentially what we are saying here is that this individuals small z, small x and small y belong to S, whereas this individual capital X belongs to 2 raised to S, right. So, in that sense we are dealing with two different kinds, and the membership or belonging to a certain kind can itself be regarded as a unary property which can be expressed by is individual is subset. For example, we can have two different, we can expand our signature to include these two first order properties, which say that for any variable x, x is ind of x is true if and only if x belongs to S, and we might say that is subset of x is true if and only if x belongs to 2 raised to S, right, belongs to the power set. Then when we do this, then it is not any more necessary to distinguish, to syntactically have different symbols for the various variable various uses of variables, and in fact we can agglomerate all the variable sets Vi. So, we can just take V, the set of variables, to be just this Vi for all the sets 1 less than or equal to I less than or equal to k. However, but what we need to do therefore is, when we use quantification, we need this implicit information to be used, right. So, then every quantified formula of the form for all I xi phi should be replaced by the one sorted formula for all x. If x is Si, then phi, where, and now recursively we need to transform all the quantifiers inside phi also to the one sorted case, right. Similarly, for every quantified formula of the form there exists I xi phi, we replace it by the one sorted formula there exists x such that is SIX and phi, where again in phi we replace all the quantifiers by this qualification. So, you can think of this as sort of bounded. So, this allows, so this essentially is like a bounded quantification which specifies the type of each individual or membership in a sort. It specifies it as a unary predicate. Yeah. So, types that way, and this is very similar to the notion of types as sets in programming languages, and we are essentially using this membership as a unary property of of an element. So, it is possible to prove that all models of an S sorted predicate logic have corresponding images in the one sorted predicate logic with this expanded signature. And therefore, it is possible to show that if any second order logic may simply be reduced to a first order logic in this two step reduction. So, there is a two sorted logic with which is in turn reduced to a one sorted logic by introducing by expanding the signature to include these membership predicates or property type properties, if you like. This kind of reduction of second order logic to a first order logic of course does have a cost. I mean, certain theorems like the Löwenheim-Skolem theorem no longer begin to hold, but models can be exclusively constructed. And in fact, it is this property that is used in logic programming to do all kinds of higher order programming also within the domain of a first order resolution. But of course, this kind of reduction applies only to a fixed finite nth order logic. So, for any given n, the nth order logic, so for any given n, the nth order logic of a one sorted signature may be reduced to an n sorted logic and which may in turn be reduced to a one sorted logic with an expanded signature. Which includes unary predicates specifying membership in the sort. And of course, correspondingly all the quantified formulae have to use this transformation which specifies the sort as a unary predicate. Yeah, that is how one would take for any n. However, this is not true for all n, in the sense that if you look at higher order logic, it transcends any fixed bound of n, and therefore a higher order logic allows for arbitrary sorting of uh, arbitrary creation of subsets indefinitely, infinitely. So, so whatever I am saying refers to a fixed n. Yeah. So, by an inductive process, we can actually reduce any, for any fixed n, any nth order logic can be reduced to a first order logic with an expanded signature which specifies the hierarchy of types in the quantified formulae, and appropriately what it does is that every formula in that nth order logic goes through a transformation process which specifies which actually transforms every quantified formula in this fashion. Yeah. And so, and otherwise the reasoning mechanisms for all these logics are more or less whatever is there in the first order case. Certain decidability issues become important. So, it is not true that decidability uh, uh, by this reduction you can reduce all decidability also to first order decidability, because that has certain special problems associated with it. Yeah, for example, so we will not actually consider those things, but you can see that in its essence all reasoning mechanisms, as we looked at in our first lecture, we spoke about validity of arguments, consistency, matters of truth and falsehood, and reasoning. All those reasoning mechanisms essentially carry over from first order logic to other nth order logics. And with that, I would like to actually conclude this session, and I hope you will be able to expand your knowledge further about higher order logics with using this set of lectures as a basis. Right, thanks.